This next video deals with phases of matter, okay? You have a table there, and a lot of the notes in this chapter have been given to you because they're things that you may have studied a little bit of, but it's just easy for you to read. There's nothing new for me to tell you. You just literally have to read it and know it, and it's better for you to read it than for me to read it to you, all right? So getting the idea of the kinetic theory of matter, saying that all substances are made of atoms and that these atoms are in continuous motion at random speeds and held together, okay, depending on their phase of state, okay, the phase that they're in. And so we have, different definitions here for these three states of matter. We're only going to consider these three. For your notes, okay, what you need to have and understand is that the main modes of kinetic energy, right, for solids is just vibrational, okay? Also that the potential energy increases, all right, as you go from solid, liquid to gas, and the reason for that is that the distance between the molecules increases, and therefore we know that increases the potential energy. Also, just having an idea of the density of water being 1,000 kilograms per meter cubed. For air, it's approximately 1 kilogram per meter cubed, okay? This is a phase change graph that you were looking at right now, so you should be able to label the major portions of this graph. So here, we just have heating, okay, of a solid. So you're going to use MCAT right here. Here, we have no more temperature change, okay? So what we have is a phase change, and you could probably guess that it's going to be melting or solidification, okay, depending which way you're going. So, you're going to use your Q equals ML fusion here, all right? And here we have heating for a liquid, okay? So write that along this line here, heating of a liquid. And so again, you can use Q equals M times C times delta T. Now substances, don't forget, have different C's depending on their state of matter, right? In other words, their specific heat capacities change, so you can't just assume that for water, the 4.186 joules per kilogram per centigrade, that will stay the same for when we're talking about solid phase or gas phase of water. So finally, this final step here, there's no increase in temperature during a phase change, by the way, okay? So what we see here is evaporation or condensation, depending on which way you're going. So I'm going to be going up here, so we're sticking with evaporation again. Q equals M times L, vaporization right there. And finally, we have the gas phase of our substance, and what this is just going to be our Q equals MCAT again, okay? So you should know the different points along that, okay, as we're adding more and more thermal energy to the system, all right, the temperature's going to increase, and we're going to see that kind of a pattern. Now, you are expected to know, okay, what happens in terms of the process of phase changes of molecular behavior when we're going between these different stages. You need to understand why our temperature doesn't change during a phase change. It's explained there, okay? And also the molecular behavior behind evaporation, exactly, what's happening when a substance, when there's evaporation that's occurring, and what that actually does to the thermal energy of the system, decreases it. It's really interesting, okay? As well as the factors affecting evaporation and the difference between evaporation and boiling as well. Two very different physical processes. So, moving on here, okay, since we've just talked about phase changes, we've got a new equation here that I actually have not completely explained yet, all right, and that was from the phase change graph. Again, you might have been wondering, Mr. Troyman, I haven't seen Q equals ML before, what are you even talking about? And what I was talking about is the amount of energy required to cause a substance to change its phase is this idea of latent heat, okay? And we have something called specific latent heat, which is very similar to our specific heat capacity. So this is the amount of energy per unit mass that we need to change the phase of a substance at constant temperature and pressure. Okay? So the symbol for this is L, and the units are joules per kilogram. And the equation that we have for it is that L is just equal to thermal energy per mass required for a phase change. Another way that we rewrite this is Q equals M times L. And we have two different latent heats. We have latent heat of fusion and latent heat of vaporization. So latent heat of fusion, all right, this deals with melting and freezing. And latent heat of vaporization, all right, deals with boiling and condensing. And actually, you know what? Go back to that phase change diagram. I would like to change something. Instead of saying evaporation, we're going to call this boiling right here. Okay? So there we go for that. Okay. So you have the idea here for what latent heat is. Okay? We call it latent. You think of the word latent, something being hidden. You know, we're adding heat to a substance. We don't see the temperature changing. Therefore, we don't have a direct measurement of what's happening there, except for knowing that the phase is changing. Okay. So the first question here is how much energy is needed to change 500 grams of ice into water? We need to assume the ice is already at its melting point. So we got to consider the story that we're telling here when we deal with thermal physics. It's all about accounting. Where does the energy go? Kind of like in accounting, where does the money go? Well, with thermal energy, you got to check where the energy goes. All right, so again, the story here is that we only need to know the latent heat of fusion for melting this ice, okay? But let's say, and this is the equations that you solve that, let's say that the ice starts at negative 15 degrees Celsius. Well, we now need to know both the thermal energy required to raise the temperature of that substance and the thermal energy required to melt it. So when we look at this type of a problem, okay, the second part, thermal energy required to melt it, is just MCAT. What we end up doing is we add the Q's, okay? So we add the thermal energy from the first part, which is to melt it, and the thermal energy to raise it to that temperature at which it can be melted. And that's how much energy is required there. Again, it stays the same because of the sig figs, all right? Let's take a look at another example. We have a pan with 0.30 kilograms of water. It is at 20 degrees Celsius, all right? And we're heating it at a rate of 400 watts for 10 minutes, okay? So what we want to know is how much mass, or how much water, okay, is going to be turned into steam as a result of this heating process. So what we assume is that all the heat goes into the water right off the bat. An unrealistic assumption, of course, but for this first introductory calculation, it's the best way to go. So what we're looking for is the mass of water into steam here, okay? These are all the givens that we have here along the way. We also need the latent heat of vaporization for water, which I have listed later. So the story is that we need to heat the water to 100 degrees Celsius, then it will boil. Well, what's the total thermal energy that we're going to be adding in this process? We can get that from the relationship between power, thermal energy, and time. And we know the rate at which we're heating this water, and we know for how long we're heating it. So we can get the total thermal energy that's going to be added. That kind of gives us our thermal energy budget, if you will. All right. So from there, is that going to be enough to get us to 100 degrees C? Well, if we do MCAT for the amount of water we have, we see that we need 100,000 joules to get to 100 degrees C from 20 Celsius. So yes, we have enough thermal energy to do this. So we will be making some steam. So how much steam exactly are we going to make? Well, if we take the rest of that thermal energy, okay, which is just 140,000 joules, and you solve for mass based on the latent heat of vaporization of water, what we end up with is 0.062 kilograms of water will have been boiled at the end of this process. Okay? So again, this is telling a story. And you do need to have some awareness of what happens in the physical world. No classroom can give you that, alone, hopefully. What I'm saying is that you can see this, you can imagine it. Go boil a pot of water and just think about what are the things that are happening along the way. All right? Yes, your teacher just told you to do that. Go boil a pot of water. Anywho, I got 3 more problems here that are a lot of fun. I think we'll continue those in class next time.